Alright, here we are again for yet another lovely day of CENG 3306 Mechanics and Materials. And this time we are recording at the correct time of day, nice and early-ish in the morning. I wouldn't call this early, but it's definitely earlier than we did yesterday. So, let's see. We have two lessons we're going to get through today, but first I'm going to work on lesson 27 for the course, and this is the second lesson, or the second lecture in elastic bending. We're going to be going over section 6.4 in the Hibbler text, and our learning objectives for here are twofold. One, we wish to use the elastic section modulus, which we designate by variable S, and beam tables to design the lightest beams, and then explain the standard notation for beams in the steel tables. So you all are going to learn about some real fun mechanicals. I'm sorry. This is CENG 3306. Okay. Anyway, let's look at some. I want to start by doing a bit of a review from the last lecture over flexural stress. So let us look at this. So let's do a bit of flexural stress review. Flexural stress review. Let me check something. Yep, we're good. Okay. Always gonna be paranoid about that. Okay. So flexural stress review. From the last video we saw, or from the last lecture we saw, that the stress along the axial direction of the beam, the sigma x from bending, is governed by this formula. Sigma x is equal to negative my over I. Negative my over I. Negative my over I. Where sigma x is the stress along the longitudinal axis, m is the moment, the bending moment in the beam at that particular point along the length of the beam, y is the distance from the neutral axis, or the distance from the neutral surface, and I is the moment of inertia of the cross-section of the member. So again, we have our little stress diagram here, and if I were to draw this out, I would simply say it would look something like this. Blah, 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 blah. You've seen this before. Let's see, let's get rid of that. And like that. Okay, and this is going to be your sigma x, and then the neutral axis will be measured in the middle here. Will be at the middle with the 0 point of this, the point where we have zero deformation, and y is measured upward from the neutral axis. And the assumptions behind this, remember there's a few assumptions built into these things. And like all equations, we have to list our assumptions, or at least we should be aware of them. Assume. So this is built on a few assumptions. For one, we're assuming straight members, or straight beams. We're assuming constant cross-section. Homogeneous. Elastic, so linearly elastic material. Elastic. And finally, plane sections remain plane. That's something you hear. That's something you hear a lot in structural engineering. Plane sections remain plane. In other words, they don't become part of a boat. Yeah, sure, why not? Okay. Anyway, so we're also assuming a few other things. Actually, not these. I wouldn't really call these assumptions. These are more just notes. So let me put those in a little different colors to make sure I'm not listing those as assumptions. So here, just a few notes. One, the neutral axis, NA, corresponds to the centroid if you have elastic bending. If you, oh my goodness, centroid, if this is elastic. And I, the moment of inertia, is a measure of geometric resistance to bending. In other words, it is a measure of a cross-section's ability to resist bending, of geometric resistance to bending. It depends nothing on the material properties, only on the geometry of the cross-section. Is a measure of geometric resistance to bending. In other words, there are certain geometric properties that intrinsically make better beams. There are certain shapes, certain geometries that are more efficient at resisting bending than others. For example, if we consider a very inefficient shape, imagine we built a beam for some reason like this, say like a horizontal board. That would be one of the worst cases you can imagine. And then you load it from the top like a simply supported beam. This would be a very inefficient shape. For the weight, this would have a very low moment of inertia relative to its cross-sectional area. So this is a very inefficient shape for bending. A vertical rectangle, I don't want to go quite that high. A vertical rectangle is a bit better because now at least we're spreading some material further from the centroid. And something like the classic W section or I-beam is even better because you're concentrating a great deal of your area far away from the centroid. But that's neither here nor there. A few other things to review from yesterday. Sigma max. The maximum stress is going to be equal to negative MC over I, where C is the distance furthest from neutral axis. Distance further from neutral axis is the distance furthest from the neutral axis. Again, C is your C is your distance from the centroid to the furthest fiber in the material. Got that? Okay. So now I would like to create a bit of analogy. So just like when we looked at previous things, we tried to find similar analogies between sometimes different topics. I would like to make an analogy between bending and torsion. You've seen torsion, hopefully you're all familiar with that by now. But let us look at an analogy between bending and torsion. Bending torsion analogy. Okay, so let's consider if it's elastic. Say we have an elastic, say we have systems that are, they're going to be loaded well within the elastic range. Well, our shear stress, our tau, is going to be equal to T rho over J. This is our shear stress. T is our torsion. Well, let me actually just write this whole thing out here for bending stress as well. Sigma equals my over I. Here, your torsional load is analogous to your moment. Just like we use a torsion diagram and we use a moment diagram to find these. Rho, this would be your outermost, this would be the distance from the center. Y is the distance from the centroid. J is your polar moment of inertia, and I is your area moment of inertia. And then the stresses tau and sigma, so shear and normal. So both of these have a linear distribution, we have seen in the elastic case. So both of these have a linear distribution. So they are very similar. except obviously one is a normal stress and one is a shear stress. And so J is analogous to I. And they both can be thought of as cross-sectional resistance to deformation. Cross-sectional resistance to deformation. Okay. Next, I would like to define a new quantity that you haven't heard before. Well, maybe not before. And this is going to be S. Capital S. This is the section modulus, or more particularly the elastic section modulus, or often just referred to as a section modulus. You can also have a plastic section modulus, which is something different. But S can be defined as the elastic, let me put that in parentheses because you don't always need to have the word elastic in front of it. Section modulus is usually just fine. That's why we use the variable S for this. Sometimes in steel design we see a plastic section modulus, but often that's not as prevalent. Okay. And S can be found by a very simple formula. S is simply I over C. It is a section property. So it's called section modulus. And this is, and again, elastic. This is the elastic one. It is a geometric property. It does not depend on the materials whatsoever. And the real neat thing about it is that it makes it very simple to find the maximum bending stress in a member. Because we know that as long as a section is under elastic bending, as long as it is, we know that the maximum stress will occur at the distance C. It will occur at in other words, the further you are from the center, the higher the bending stress. So we can simply say, you know what? Let's just combine the moment of inertia and the C, and we can then from then on simply say sigma max is just M over S. And this makes designing beams very simple. Well, as long as we know all the difficult parts they take in steel design, but let's not worry about that. And also concrete design, of course. Okay. So here, M over S, what this is basically saying is we have distilled everything about the geometry down to a simple variable S. All we have to do is we can look up S in a table and literally just divide the max moment at that location in the beam by the section modulus, and that's the max stress. That's it. So that's what's so powerful about this tool. Okay. So if we look at this from the point of view of design, let's see here. Design. Let's consider designing beams. Beam design. Well, we're going to say that actual must be less than or equal to allowable. That's the governing equation for this entire course. Actual is less than or equal to allowable. Or allowable if you prefer. And what does that mean? In the context of beam design, our actual is going to be a normal stress. So sigma max actual is less than or equal to sigma allowable. And then we can say, okay, what is sigma allowable equal to? Well, that's going to be sigma fail, the failure stress, over the factor of safety. But what is our failure stress? That is usually just our yield stress. Although maybe if you are more, well, actually, we have to be very careful with that. All of our analysis so far is assuming elastic. Sometimes you can design to the higher ultimate stress or something like that, but then you're dealing with fully plastic bending or partially plastic, which we'll see later. Okay, and then M max over S is less than or equal to sigma y over the factor of safety. Or in terms of beam design, if I go and distill all of this down and basically rearrange this, I can say that for the purposes of beam design, that S, the section property, must be greater than or equal to M, the moment, at that section, or mainly the max moment in the beam, times the factor of safety divided by the yield stress. And this is what you actually use to choose a cross-section. Okay, so, and how do we find the cross-section? How do we find the cross-sectional properties? Well, you can either calculate them yourself, simply by calculating I, or more often, you'll actually have a table of selected shapes. For example, you can get them from, see the beam table, select beam from Appendix B, page 804 in the Hibbeler text. In the Hibbeler text. So, let's see. Let us talk about standard shapes. I want to talk a bit about standard shapes. So, in other words, we have beams, and we have various beam sizes in the beam table, and we wish to be able to select them. Okay, so let me talk a bit about standard shapes. So the beam table will have, I don't have an example in front of me, but let me just quickly show you what I mean by beam table. Let's see, so I'm going to Google, which is probably not good form, but let me show you this. Let's see, AISCW sections standard table. If you can, oh, I do not have internet right now. Give me a minute here. I'm still recording. Okay, now it's just plugged in. It should be going. Just a moment, please. And we should be going. Okay. Well, that's a full database. You don't necessarily need the full database. Well, maybe. Okay, so let's open this up, and I actually have this as an Excel file. That's fine. You can get this directly from AISC. For those who are not aware, the AISC is the American Institute of Steel Construction. They're the ones who put out the AISC manual, which is sort of the Bible of steel construction. For those of you who will take my steel and concrete design course, you'll be getting to know that very well. So if you notice here, you have a big database of all sorts of different sections. And at the top we see W sections, and I will explain later what these are. And then you see S shapes, HP, C channels, MC channels, angle Ls. Basically there's a whole bunch of different types of shapes, and I am going to define a few of these and what they mean. But if you look along here, what they have is, they basically have what this database represents. This is a catalog. This is a list of standard shapes. In other words, if you are designing a building, if you are a civil or a structural engineer, you can actually call up a steel mill and say, okay, the standard shape, I want 1,000 feet of W40 by 264, and they'll say, okay, it'll cost this much, etc., etc. Or sometimes if they're more, there are certain shapes here that are more common than others, and you're probably usually better off buying one off the shelf than having them custom rolled. But anyway, in order to actually manufacture these, they have to roll them they're hot rolled. They're rolled in a series of rollers while the metal is red hot. But in order to make each of these, they basically have a standard set of dies that that form each of these. But anyway, so again, the AISC manual is put out by the organization that puts this together is basically a consortium of steel manufacturers. So they want you to use these shapes. I mean, this is basically a catalog. You can go buy these. It's just like the world's most underwhelming Christmas catalog, but it is a catalog. And so if you notice, look at the and they just have all sorts of properties here. So they have things like the weight, they have the cross-sectional area, the depth, a little bit different clarification on the depth. Flange width, another measure of the flange width, thickness of the web. Let's see, some other properties that I can't explain without getting too involved. another section property here, just the ratio of the beam to the thickness of the flange. That's useful for steel design. But then, look here. This is stuff that you're more familiar with. This is, the Ix is the moment of inertia. This says Ix in case you can't see it on the recording. This is Ix. And this is the moment of inertia along the strong axis. They also have moment of inertia along the Y, which is along the weak axis. In other words, if you have a beam here that is like this, if your normal loading vertical is going to be strong axis bending along your XX axis, because that generates stress along the XX axis. Your weak axis bending would be if you have lateral loads coming in from the side, and so certain shapes are better at resisting that than others. But generally, the shapes obviously have a strong and a weak axis, and you can see that here. Among other properties, they have what we just learned about today, the S. So really, if I wanted to, back up. They also have Z, which is the plastic moment of inertia. Hey, look, the polar moment of inertia, and just all sorts of fun properties that you can just go on and on and on for days. But usually you don't need to use all of these when designing. For our sake, we're mainly going to be concerned with, and hey look, radius of gyration. Sorry, I just get distracted easily by steel sections. It's just like shiny. Okay. Okay. Now, squirrel. Okay. So again, this is what we're mainly going to be using, the S for our design here. If we're concerned with elastic sections, we're going to go to S, which we're going to go to the S column, which is the elastic section modulus. And really, all you then have to do is you simply find the shape that a shape that has the minimum required S. Now, what you would do is you would also want to select for usually you want to select for the lightest shape possible, which means that I'm going to go through a table of this later, but this SW36, 36 is the depth, 182 is the pounds per linear foot. So in other words, this is a 36-inch deep beam that has that each foot of the beam will weigh 182 pounds. And so what you would do is you would go through here and you would try to find sections. You would try to find the lightest section that would have the minimum value of SX. And that's really how you design. Now, when you actually take a steel design class for my civil engineering students, there is more to it than that. This is definitely a simplified thing. This is definitely a simplified analysis. When you start dealing with longer spans and higher loads, you start dealing with beam buckling and lateral torsional buckling, and there's other ways beyond simply elastic bending that a beam can fail, and that's what you study in steel design, but we don't need to worry about that in this class. That is beyond the scope of this course. So, but all we're trying to do here is exposure to the basic idea of beam design. Okay. So let's look at some standard shapes here. Standard shapes. I want to talk about some families of standard shapes. And I'm going to discuss 4 of them. Okay, so let us look at well, first I'm going to talk about wide flange sections. These are your W sections. They are not I-beams. I-beams, people sometimes refer to W sections as I-beams. They're wrong. I-beams haven't probably been used widely since the 1930s. Wide flange shapes, wide flange or W section. Sometimes people mistakenly call these I-beams. They are not I-beams. If someone calls them an I-beam, feel free to whack them with a giant wrench. Okay, so we have a shape like this. An I-beam, in contrast, would have a very narrow web. So we have something like this. It's not actually made of 3 plates like I'm kind of drawing. We sometimes do actually make members like this, literally welded together by plate. Huh?
You see wooden ones that are 3-piece.
Yeah, you sometimes see like wooden beams that are 3-piece and things like that, but really, if I were to draw this properly, they would be more like there's actually a fillet here, like a slight curve, and that's because these are actually formed by rollers. You have big rollers that come in and squeeze the section in together slowly. Okay, bit by bit. Now let's see here. We have a beam depth D. So I want to illustrate some of the properties of this section. We have the beam depth, which will use variable D, and then we have the flange. The flanges are the plates at the top and bottom. Flange, and web. Flange, and web. So this is the actual value of D. But we label these according to something like this. We'll say something like W30 by 300. So what this means is, this would be, say, like the nominal depth. Nominal depth. The W, again, is the shape indicator, shape type. So W tells you that it's a W shape type. And 300 is the approximate weight per foot. So pounds per, my arrow is going the wrong way. Usually, so this is the weight, the linear weight. Usually, at least in American shapes, is pounds per foot. Pounds per foot, that's a very nice, that's good, strong American steel. It comes in pounds per foot. This metric. Okay, again, so this is the nominal depth. What do I mean by the nominal depth versus the actual depth D? So I can say the nominal depth is approximately D, but it's not actually equal to D. What I mean by this is it's approximately equal to D. And what do I mean by this? Well, okay, these are names that are used to these are catalog names. These are names used to select shapes, and literally sometimes even over the phone. So it wouldn't really be good to say, oh, I want a W 30.291 by 300.8 or something like that. If you look here, if we go back to the database here, we will see that if I go to, say, the W33, let me see if I can find, where's the actual depth here? See, look at this. All of these are in the W36 family. See this? All these W36s here. But if you look at the actual depth, this is basically the depth rounded to a fraction. This is the closest actual depth as a decimal. And so some of these are like up to, so we have this W36 here is actually a 37-inch deep beam. This W36 here is actually a 40, well, that one's a bit odd. Some of these get really bit off, but that happens. So that is the approximate depth, but when you actually design, you want to use the actual depth, not the approximate depth. This is just to indicate the beam family. Okay, so let me then indicate some other families of shapes. There is another family of shapes which you sometimes see, less as W sections, but there is one called S sections, which are called American Standard, which have their own history behind them. So there's also, let me label this in purple. Possible. I'm not quite sure the history behind that. It might be named after the company, but I'd have to look that up. American Standard. Okay, so these have a slightly different shape. It's more of a tapered kind of flange like this. And then maybe one of my lovely drawings. A more pronounced taper, so it's really obvious it's not just a couple plates welded together. except this part should really be horizontal. The top and bottom are horizontal. The rest are definitely not. They're meant to be curvy. Well, they're meant to be smooth curves, not my crappy curves. But anyway, so an example for this, the letter we use for this is S. We use American S for standard, because nobody's actually going to make an S-shaped beam, because that would be a god-awful way to design a beam. S16 by 150 is an example of is just one example of an S-shaped beam. We can also have C channels, or just channels. So we can have a channel, which is really can be thought of as this is also a rolled shape, but it almost looks like just like a single plate bent, but it's a rolled shape as well. And it's like this. So it's a C shape, although it's definitely more of a rectangular C than a smooth curve C. Again, I don't know why you would try to make a beam that's literally shaped like a C, but I'm sure if you really had enough money and you really wanted it done, I guess you could get it done. Ultimately, you can get whatever you want made if your pocketbook's big enough. And the depth is measured like this, and this is indicated by something like something like C12 by 75, where it's the same kind of naming convention as the W sections. This is approximately equal to the depth, and this is the weight per foot. This is the weight per foot. Okay. And finally, one other shape family. And there are others that we haven't talked about, but I'm just trying to give you some. I'm not trying to present a full steel course here. I'm just trying to give you some exposure to this stuff. So I'll just indicate it here. But angle, a third main type of shape, a fourth big type of shape is angle irons. Angle, also sometimes called like an L bracket or something like that. And well, this one's fairly simple. It just looks like an L. And different shapes have different advantages, pluses and minuses. Some are better for bending, some are better for shear, some are better just for being cheap and light. It just depends on what you're building. So this one is a lot different naming convention than this and this. This would be something like L8 by 6 by 5/8 by 5/8 inch. Because this actually is made of a bent plate. 5/8 inch. And so these are the length of legs. Usually the thickness on each of these will be exactly the same because they're formed from the same piece. Length of legs. And this is the thickness, the material thickness. So in other words, it would be like 8 inches, 6 inches, and 5/8 inches thick. M, thickness. Thickness does not start with an M. Okay. So let's move along. Let me do you got that? Okay. Let me do an example of analysis rather than design to start out. So let me work through an example of analysis rather than design. My first example will be analysis rather than design. Example 1. Okay, so let's say I have a beam with a loading, and you know what, I'm going to cheat again by just giving you the reactions right off the bat. I think you know how to find reactions at this point. If you don't, oh boy. Okay, so we have a pin and a roller. You know how to find reactions at this point, right? Okay, good. Okay, just checking. Alright, so let me go and I will get the I'll show you the loads on here, And then I'll also just go ahead and show you the reactions, although usually you'd have to find the reactions first, but again, that's trivial static stuff. You know how to do that. 2 kilonewtons per meter. I'm given this, and I wasn't given the reactions, but I've solved for them. So this is 10 kilonewtons. 6 kilonewtons. And 4 kilonewtons. And then, let me label some points. That will be nice to have. So this is going to be A, this is going to be B, C, no, actually, B is going to be in here somewhere, sorry. B will be an internal point that we'll use later. C, D, and E. And then here, this is going to be 4 meters, 2 meters, 3 meters, and 3 meters. And this is going to be, and I'm actually given the cross section of the beam. I'm actually given the cross section of the beam, and told that it has the following properties. It is 100 millimeters in width. It's simple. It's a very simple rectangle, and then 300 millimeters high. So I'm given all of this. Well, actually, I wasn't given. Like I said, I wasn't actually given the reactions, but I jumped forward on those just to save some time. Let's just say I'm given all this. Oh my gosh, that's a 6. And then I wish to find, or if you prefer Guyven and Find, sigma max at point B. That's why I have point B, because that's where I'm looking for the max stress at point B. Okay. Let's see. So we got the reactions. Now let us find the moment at B. So let's find the moment at B. I could create the full shear and moment diagram, but really all I need is the moment at B. So what I'm going to do is, I think this is a good use for the method of sections. So I am going to go across like this. I'm just going to cut it at B. And again, I'm going to assume positive shear and positive moment, which looks like this. Oh, that looks bad. A little better. VB and MB. VB and MB. Here. Like this. And the distributed load has a value of 2 kilonewtons per meter. And we have a 10 kilonewton point load here. Alright, and then let me label some points, maybe some dimensions. Get a nice complete free body diagram. Let's see, so 4 meters. And then points A and B. A, and then the cut at B. Finally, let me do a balance of moments. Some moments about B are going to equal, let's see, let's work through that. That's going to be negative 4 meters times 10 newtons plus 2 meters times 8 kilonewtons. Let's see, actually this should be 10 kilonewtons, sorry. 10 kilonewtons. 10 kilonewtons plus 2 meters times 8 kilonewtons plus MB is equal to 0, and we find that MB is equal to 24 kilonewtons counterclockwise. 24 kilonewtons counterclockwise. So again, this is going to be the stress in the beam must generate a 24 kilonewton counterclockwise moment. Okay. Or sorry, no, actually no, the moment is going to be 24 kilonewtons counterclockwise. And from this we will actually see where so do keep this in mind, I want to illustrate this. The moment in the beam is going to be counterclockwise because the moment's positive. But let's look at the actual stresses here. I'm going to draw that out. Let's find the max bending stress at B. Max bending stress at B. Max bending stress at B. Well, first we need to say, let me draw the section again. First I'm going to need to find I, and the dimensions here. This is 300 millimeters, 300 millimeters by 100 millimeters. 300 millimeters by 100 millimeters, and sigma max is equal to negative MC over I. Negative MC over I. Negative MC over I. And then I, if we remember our formula for the cross-sectional area, the moment of inertia of a rectangle about its own centroid, is 1/12 BH cubed. And that's good. So that's a formula you might want to memorize. 1/12 times 100 millimeters times 300 millimeters to the third, and this will equal 225 times 10 to the sixth millimeters to the fourth. Isn't that a lovely unit, millimeters to the fourth? Okay. So if then I plot out the stress, it's going to look something like this. Actually, let me put this a little bit further over. Okay. The stress is going to look something like this. So the stress is going to go in the opposite direction of the moment. So here, as we derived previously, if the stress, if the moment was clockwise, or was counterclockwise, the stress is going to be clockwise. Like that. And that negative comes out of the derivation yesterday. And so this is the neutral axis. This is the neutral axis. This is our sigma max in compression. And this is our sigma max in tension. And the distance for each of these is going to be c. This is actually a symmetric beam, so c is the same for the top and bottom. It doesn't necessarily have to be, but in this case it is. So this actually means that our stress is also, our max stresses are also going to be symmetric. So let me just write this out. Let me do it in purple maybe. Or actually red. I like red better. Sigma max for tension is going to be equal to, and sigma max for compression is going to be equal to 24,000 Newton meters times negative 0.150 meters over 2.25, basically MC over I. It's actually 225, not 2.25. No, actually this is okay. 2.25 times 10 to the negative 4 meters to the fourth. I already had the unit conversion baked into this. And then this is the same idea, except it's except C will not be negative. So negative 24,000 Newton meters times a positive 0.150 meters over 2.25 times 10 to the negative 4 meters to the fourth.
Is that at the top? Is that a negative at the beginning?
Yeah, that should be a negative there, thank you. And so this will come to 16 megapascals. And just make clear this is the max stress in tension, 16 megapascals, and the max in compression is negative like we'd expect, negative 16 megapascals. So in this case it's symmetric, although it need not necessarily be. And there you have it. Okay. Okay. So next, I'd like to continue this design. Let's see, or actually, let me think about this. Yeah, actually, let me think here. Okay. So next, I do have another example I'd like to work through here. Okay. I have another example. So that was more of a analysis example. What if I had a design example? And this one's going to be fairly short and sweet. I am given the following. Guyvan. Okay, so we have A36 steel is what we're restricted to, which the sigma y is going to be 250 megapascals. The yield stress is 250 megapascals. Sigma y equals 250 megapascals. I am told that I need a factor of safety of 2.0 with respect to yielding. And that the beam must resist 25 kilonewton meters, so slightly different than the last one. 25 kilonewton meters of moment, of max moment. In other words, on the shear and bending moment diagram, this was the this would be the largest value anywhere on the shear and bending moment diagram is 25 kilonewton meters. So I need to select a shape that will work with this. Then let's see. So I could go to the steel table, or I could, or in this case, I was actually given a set of possible shapes here. I was given, or let's say I found some examples like this in the. You know what? I'll just move on a little bit here. Select most economical by weight beam. Light weight beam. Okay. So, and let's say my choices are, I was given 3 choices, or 4 choices. Maybe this is all we have in our catalog, or all the manufacturer has in inventory, so I have to choose one of these. So I'm trying to make the process a little bit simpler. SX here is in units of 10 to the 3rd millimeters. It's not a fun unit to make a table in. So I have W150 by 30, W200 by 36, W250 by 22, and W310 by 21. And the SX are 218, 342, 227, and 244. So let's say, and this is actually fairly common on some large industrial projects. It's not uncommon when you're designing a large facility that they might say, you know what, you're going to do a lot of local analysis as you go across these things, like designing things like pipe supports, pipe racks, little equipment supports, things like that. And often there are times when there may be a lighter shape, but available that would carry the desired loads, but you don't always necessarily want to select simply the lightest shape, because often it behooves you to, because imagine if you were building a building and you had your design, your blueprints called for literally 120 different shapes. Imagine trying to manufacture that, or not manufacture that, imagine trying to build that building with 120 different shapes sitting in your yard. That's going to be very difficult. That's a construction nightmare. There's a high probability that somebody's going to screw something up and put the wrong beam in some place, and then something's not going to fit, or something's going to be overloaded, and it's going to be a nightmare. Oftentimes, and also it's going to be a lot more expensive, because if you order, the more you order of something, the cheaper it is per foot. So often it behooves you for a large project to simply say, you know what, we have a contract with a steel provider. They told us that they have, we have a ton in stock of these 5 shapes. So you know what, we're going to design the entire building based off these 5 shapes. So we know from experience that we've built a dozen buildings like this before in the past. We know that we'll be able to design the building entirely out of these shapes. So as you're going through your analysis, you don't have to worry about the entire steel manual. Just choose from these 5 or 4 or whatever number shapes. So there are cases where this happens. I've done this before. It happens pretty common, actually. So this solution is actually going to be fairly straightforward. Very easy, actually. Solution: 12 molar H2SO4. Oh, that's not right. Okay. Huh? H2SO4 solution. It's a chemistry joke. Okay. So solution, we always go back to the actual is less than or equal to allowable. And then S is greater than or equal to M times the factor of safety over sigma Y. So it always comes back to. And then that is simply 25 kilonewton meters times 2.0 times 1,000, just doing a unit conversion, kilonewtons per meter, all over the yield stress of 250 times 10 to the 6 pascals. And this says that then this comes to 2 times 10 to the negative 4 meters cubed, or 200 times 10 to the third millimeters cubed. So then, in other words, S is greater than or equal to 200 times 10 to the times 10 to the third millimeters cubed. And then we go back to our table and we say, so we need greater than 200. Well, looking at this, I'm going to select the lightest one, which to me looks like this let's see, wait a minute, something's...
I think it's backwards.
Huh?
Looks like the numbers are backwards. 30 by...
Oh yeah, sorry, yes, you know what, I wrote these wrong. This is a bit weird. I'm confusing you. Sorry about that. I'm confusing myself. Let me rewrite these in a more sane manner. I don't know why I had these in my notes like this. So W30 by 150. You're not going to see a 150 deep inch beam. That would be really weird. Can you imagine a 150 inch deep beam? Times 200. W22 by 250. And 21 by 310. So we're looking for one that has the minimum, that has the required S, but is the lightest weight. And yeah, that's going to be the W 21 by 310. No, wait. Let's see. Something's not right here. Let's see. Why does my notes say W310 by 21? That doesn't seem right. No, we go for the one that's lightest. So if we want the lightest, let us select the W. Well, actually, they all have the required S, don't they? Interesting. So of these, all of them have the required S. So I'm going to go with W30 by 150. So again, I'm going to select W30 by 150. And that's my answer. So lightest is most economical. Generally. However, we would have to be careful. The downside of this is that this is a very deep beam. This is a 30-inch deep beam. So often we can make a beam lighter, but in exchange we have to make it taller, which means in terms of, yes, it may be more structurally efficient, but in terms of, say, a building, that means basically, if you think about a building, the beams are essentially represent wasted space. If you have a floor system, for instance, in a building, if this is the top surface of the floor, then you have some decking, and then you have beams underneath it, here, beams underneath it, whatever, and maybe a drop ceiling here or some sort of other ceiling, the beams essentially represent wasted height in your building. That is space that cannot be occupied by people. It is it's useful for things like carrying cabling and HVAC and things like that, wiring, etc. But it doesn't actually help. It's not actually a usable space. So if you have very deep beams, obviously architects don't like that because you are taking away from the utility of the building. But anyway, ultimately you need to balance cost versus utility. So that's another subject entirely. All right, that will do it for this lecture. We'll be moving on shortly to work on lesson 28, which will be over plastic and partially plastic bending. Thank you.